Okay, hi everyone. So in today's video, we're going to be looking at the problem of solving this differential equation here. And this will fall into the topic of exact differential equations, where we need to find an integrating factor to solve this equation. So just to remind you, what is the definition of an exact equation? Well, that's here. So given an equation m dx plus n dy equal to 0, it is exact if there is this function f whose differential is the left-hand side of the equation. And then this equation can be checked for exactness if we have the following criterion, which is that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. Okay, so let's just go back to the original problem here. So to solve this equation, let's label the m and the n in this equation. So that's going to be this here. This is going to be, let me just change this. So this here will be m, and this here will be n. And to check if this equation is exact, we'd have to compute the partial derivative of m with respect to y. And we can just quickly do that. So because we're taking a partial derivative here, the 3x is treated as a constant. So differentiating this will just give me 0. And then 6 over y becomes negative 6 over y squared. Okay, good. Now we can look at the other partial derivative. That's the partial derivative of n with respect to x. And so here we will get 2x over y minus 3y over x squared. Okay, so these are the two partial derivatives we would have to compute, and we can just quickly see that these two things are not equal. And so that means that this equation here is not exact. So we can't immediately use the technique of exact equations to solve this differential equation. All right, so it's not exact. Now, what is the typical method we can check? Well, we can assume that there is an integrating factor which depends only on one variable, either x or y. And so I've actually dealt with this in a previous video, but just to give you the kind of flow chart of how this works, here it is. So to solve this equation m dx plus n dy equal to 0, we first compute these two quantities. So going on the left here, take my minus nx divided by n. And then we check, is this going to be a function of x alone? If it's not, then we stop and we check the right-hand side. Then we check, is nx minus my divided by m, is that a function of y alone? If it is, we continue downwards, and if it's not, we stop. So if, on the right-hand side, if my minus nx divided by n was a function of x alone, then we can create this integrating factor, and then finally solve the corresponding exact equation here. Okay, so now for this problem that we have here, this is also not going to work. These two formulas will give us, just show us that, well, we won't be able to even use the formulas. And just to kind of give you an example, well, a motivation for why. If we compute what is my minus nx divided by n. So remember, if we were tracing the left-hand side of the diagram here, this is the quantity we have to compute. So let's just take a look at that. So this here would be negative 6 over y squared minus 2x over y plus 3y over x squared. Okay, so that's what we would get. And if we had to divide that by n, so this n over here, x squared over y plus 3y over x. Well, you can just eyeball this to see that nothing's going to cancel in a way that we're going to be left with a function purely of x. So you can check this, you can multiply everything out and cross-multiply, and you'll see that there'll always be a y floating around. And so that means that in our diagram here, so in this diagram, we are not going to be able to use the left-hand side. And also, we will not be able to use the right-hand side for a similar reason. Okay, so then the question, what do we do? Well, what can we do? And sometimes the answer to this question is not obvious, and it actually requires just a bit of an observation or an idea. And this is such a situation. So if we look at our differential equation, and we try to sort of, from a bird's eye view, try and understand what was creating our problems, well, not maybe what was creating our problems, but what would make things significantly easier for us. And maybe you arrive at this idea, which is that the y's and the x's appearing in the denominators here are problematic, let's say. So if we can remove them, then we'll be in a position to solve the differential equation potentially easier. And remember, we can, as long as we multiply both sides of this equation by something non-zero, we are still solving the differential equation. So let's try something here. Let's try the simplest function, which will get rid of the fractions here. And you can see, because there's a y here and an x there, this will just be xy. And now let's compute the equation mu m plus, mu m dx plus mu n dy equal to 0. And here you'll see that if we just quickly multiply everything through, we'll have 3x squared y plus 6x dx plus, what will this be, this x cubed plus 3y squared. So this is equal to 0. So if we multiply the mu throughout, this is what we get. And because we've removed the fractions, differentiation here is going to be a lot easier. Okay, so now we are in a different situation. So let's label the m here and the n. So let's call this m. Let's call this n. And let's compute these partial derivatives again. So if we take the derivative of this here with respect to y, then since x is a constant, we're just going to be left with 3x squared. And on the right here, if we take the partial derivative of this with respect to x, well, then y is a constant. And so we're just differentiating this x cubed. And so this will also just be 3x squared. And the nice thing about this problem is that this works out. So now because we have equality here, the equation is exact. So that's just from the criteria for exactness. Okay, so this is now an exact equation. So what we can do is solve it, and let's just quickly run through that. So we can let f equal the partial integral here of 3x squared y plus 6x partially with respect to x. And when you want to partially integrate, it's really the same thing as partially differentiating, obviously opposite. But you just treat the y here as a constant. So that here you'll just get x cubed y plus 3x squared plus an arbitrary constant. Now, an arbitrary constant, when you partially integrate, is going to be an arbitrary function of y. Great. Now we can use the second piece of information, which is that if we partially differentiate f with respect to y, then we should get n. So let's differentiate this expression here with respect to y. Then we'll get x cubed. The 3x squared falls away completely because it's a constant. And then we have g prime. Okay, and now as we just said, this has to be equal to n by exactness. And that is going to mean that this is x cubed plus 3y squared. and this will allow us to go a little bit further. We can cancel here the x cubed, and we get g prime of y is equal to 3y squared, so that g of y is equal to y cubed. Great, and so that means that the final solution is just going to be, so I'll write that here, the final solution, I'll write that down below. So the final solution here is just going to be, you set f of xy equal to a constant. And what is that? Well, that's just going to be x cubed y plus 3x squared plus g of y, but we know what g of y is. That's going to just be y cubed. And we set that equal to c. Okay, so that gives you an example of where we can still use the technique of exact equations, where none of the formulas that we saw before, so I'll just go back to those formulas quickly, where this diagram really doesn't work. So sometimes we do have to just try find a clever idea or try and make some progress in some way, and we can still use the techniques. All right, well, thanks for watching, and I'll see you next time.